Go fun.
Okay, it's 9, so let's get started. Good morning. So this is basically just giving you a review on what we did last time. And some of you might have already done this chapter in your Physics 1, because this is supposed to be covered in Physics 1. So I don't know if you guys talked about waves in Physics 1 or not. Have you guys talked about waves in Physics 1? This is basically supposed to be covered in Physics 1. So last time we talked about sinusoidal waves. So sinusoidal waves are the waves produced by any object or vibration of a medium that that does back and forth motion. Okay, any medium that does back and forth motion produces sinusoidal waves. Or I should say source. Any source that does back and forth motion, it produces sinusoidal waves. So can you guys give an example of a source that produces sinusoidal wave? Any example of a source that produces sinusoidal wave?
Like a pendulum?
Pendulum, yeah, pendulum produces sinusoidal wave because it does back and forth. Any other example? And in Physics 1, you guys talked about simple harmonic motion. So what is simple harmonic motion? Simple harmonic motion is back and forth motion. So when an object does back and forth motion, it produces sinusoidal wave in a medium. So sound is also kind of sinusoidal wave. We'll talk about that in a second. Okay. So any object that, or any source that executes sinusoidal motion produces sinusoidal wave by disturbing the medium. Okay. And a sinusoidal wave could be represented by this kind of sine wave. Okay. And again, it's produced due to the oscillation of a source back and forth or to and fro, which we also call simple harmonic motion. Okay. Now let's talk about some of the terminologies that we used in simple harmonic waves. So this is a simple harmonic wave produced by simple harmonic motion of a source. So we have the peak, okay, peak of the wave. We call the peak of the wave crest if it is positive peak. If it is negative peak, we call it trough. So crest is positive peak, trough is negative peak. Wavelength is the distance between peak to peak. Okay. So from one peak to another peak is wavelength. And this wave is traveling at some speed that's called wave speed. This whole wave is moving to the right at some speed v. The maximum displacement of the wave, or the maximum height of the wave, is called amplitude. Okay, so that's amplitude. So the distance of crest from this equilibrium is, from this baseline, is the amplitude. Okay, so this 0 is the baseline, 0 mark, and that's the maximum displacement. And this maximum displacement is amplitude. You guys might have seen this in simple harmonic motion also, Physics 1. Okay, so amplitude is the maximum displacement, and If it is positive maximum, then we write A, positive amplitude. If it is negative maximum, then we write negative A or negative amplitude. Okay. So simple harmonic motion is repetitive, just like simple harmonic motion. So in simple harmonic motion, object starts from some equilibrium, it goes to forward duration, then back, the other side, and then back again. It does this all the time, okay? Like pendulum. So it does this back and forth motion repetitively. Like that, the wave also, the simple harmonic waves are also, or sinusoidal waves are also repetitive, okay? So it starts from here and then completes that, and then again it starts again over and over, okay? So this is the wave in the beginning, wave sometime later, wave sometime later, and this one moves forward, and then you get new wave, you create new wave, okay? So you get the same repetitive wave, okay, as the wave moves forward. So this one moves forward, and then you get a new wave, moves forward, and then you get the same new wave. So you get the same pattern over and over in sinusoidal wave, just like simple harmonic motion. So starting from here, okay, to here, from peak to peak, is what we call wavelength, and it's also called one cycle, okay? One wave cycle. So one wave cycle is produced during one complete oscillation. So this is produced by some kind of movement of particles or oscillation of particles, and during one complete oscillation, the source produces one complete wave. So starting from here to here, okay, so that's one complete wave produced during one complete oscillation. So when let's see, maybe I can show you a simulation that will make it a bit more clear. Just a second. Let's see. Okay, let's look at this in slow motion. So here, this is the source of the wave. So as it moves up and down, it produces wave in this medium. So this is the medium. Okay, the beats are the particles in the medium, and this is the source. When the source goes up and down, you produce the wave. And in one complete oscillation is starting from here, going up, back again, and down, and then back again to the same point. That's one complete oscillation. In one complete oscillation, it produces one complete wave. Okay, so let's look at that from the beginning. So we start. So it starts from here. If I see that, so little bit went over the starting point. So starting here, up, back and down, and then back again. So it completes one complete wave. So this is one complete wave. A little bit more than that because of this extra movement. Okay? So let's look at that one. So up, back, down. Okay? So this executes one complete oscillation, and in one complete oscillation, it produces one complete wave. That's one complete. And the length of one complete wave, this is wavelength. Okay? That's the wavelength. And the time it takes to make one complete wave, okay? How much time it takes to make this one complete wave, that's the time period. So time period is time to make one complete wave, or you can also say the time it takes to make one complete oscillation is also time period. So time period is starting from here to here, back to the same position, and then down, and then back again to the same position. That's one period. Or the time to make one complete wave, that's also period. So this is again simple harmonic wave. So this is simple harmonic wave, and the motion of this source is simple harmonic motion, which is what you learned in chapter 14 of this course in Physics 1. So simple harmonic motion of an object produces simple harmonic wave in the medium. And any wave that shows this kind of structure shape could be represented by either sine or cosine. Okay, so this is the height of the wave at any position. Okay, at any position, this formula gives you the height. So if you want to know what's the height of this wave here, okay, so you plug in the height here. The position here. So let's say 1 centimeters. You put 1 centimeter there, and then this formula will tell you what the height of this wave is. So you want to know what's the height of this wave at this point. Okay, let's say at that point. So what's the position? So let's say the position here is 0.5 centimeters. So you plug in 0.5 centimeters there, and that will give you what the height is. So this height is what it will show. Okay? So in this formula, A is amplitude, maximum displacement. So A is that, or that, or that. All these are maximum displacement or maximum amplitude. So that's A, amplitude. And lambda is the length of the whole wave. Okay? So there are a bunch of ways you can interpret or you can find the wavelength of the whole wave. For example, so you can start from here and then there. So crest to crest is one wavelength, or that's the distance is one wavelength. That's this distance. Or you can also say distance from trough to trough. That's also same as that. Okay, one wavelength. Or from here to here. That's also one wavelength. So they are basically all equal. So distance from here to here, or from here to here, or from here to here, that is lambda, one wavelength, distance of one wavelength. Okay? So this formula tells you the height of the wave at any position, x. So this is the snapshot graph. This is the histogram. Okay, histogram. Height versus time gives you histogram. Histogram means this tells you how the medium is oscillating. Okay, the particles in the medium is oscillating. So this graph is. Let me show you the simulation again. So let's say this wave is moving to the right, okay, and let's say at some time, okay, I'm looking at my watch, and then at a particular time, I took a picture, okay, I took a snapshot like that. So this is the wave at a particular time. We call this snapshot graph. Okay, snapshot graph is graph at one particular time. Let's say at 5 seconds. At exactly 5 seconds, I took this picture, and this is snapshot graph. Now, history graph is just focusing on one single point. You focus on either this point or this point or this point. Focus on one particular point, and then see how the height of that point changes with time. Okay, that's the histogram. So let's say I will focus at one point, okay, this point, this green point. So, and I'm looking at my time. So it's here and then down, here and down. So you plot the height of this green dot with respect to time. That will give you the histogram. Histogram is how this medium, particle in the medium, is moving. Okay? And last time we learned, I don't know if you guys got time to watch the video or not from last lecture. We learned how to convert from snapshot graph to histogram. Okay, so if you don't remember what I'm talking, so last time we learned how to convert from this one to this one, or here. So this is the histogram. Sorry, this is the snapshot graph, and you can convert this snapshot graph to histogram. So this is height versus time. This is height versus position. Okay, so you can change this one to that one. Now, if you change or convert the histogram, sorry, the snapshot graph, if you convert the snapshot graph of sinusoidal wave, okay, if you convert, this is the y versus x, so this is a snapshot graph. Snapshot graph is again graph at a particular time, okay, a picture at a particular time. Now, if you convert this to a histogram, which is y versus time, okay, so that's the histogram, you get exactly same graph, right? Because you see, in histogram we focus on a single point. Okay, so for example, let's focus at this point. Okay, so initially it is at this height. Okay, and then as time passes, the particle will be lifted up to that height, and then at that height, that height, that height. As it moves forward, the particle here would be lifted to the height equal to the shape of this curve. Okay, so the shape of this curve here is at 0 time is that. So the displacement of this particle, the particle is here, is that. In the next instant, sometime t later, the height of this particle would be here, okay, that height. So as this wave moves to the right, in the next instance, that would be the height, that would be the height, that would be the height. Okay? Which, if you plot, would be exactly the same as the snapshot graph. Okay? So again, in the beginning of the time, that's the height, and then sometime later, that's the height, 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 sometime later, that's the height. So you're plotting height at different times. So you look at one single point, okay, this point, and then see how the height of the particle in the medium changes with time. And then you get this. Okay? I will post some of the homework problems on this. Do a little bit more practice on this to get used to converting from snapshot to histogram. Okay? So I just explain what time period is. Time period is time to make one complete wave cycle. So starting from here to here is one complete wave. And the time to make one complete cycle is time period. So again, it could be from here to here also. So this is one complete cycle. So that's time period. Another way to interpret time period is the time to make one complete wavelength. Okay, so from here to here is one wavelength, and the time it takes to complete one wavelength is time period. So time period is time for the wave to complete one wavelength. And frequency is how many complete wave cycles you produce in 1 second time. Okay, so from here to here, so this is one complete wave cycle. So how many such wave cycles you make in 1 second? That's the frequency. Or how frequently you generate wave, that's the frequency. let's say you generate 1,000 waves per second. Okay, so you generate 1,000 waves per second. So that's the frequency. The frequency is, we express this as 1,000 hertz. Okay, so 1,000 hertz is you are generating 1,000 waves every second. So in 1 second time, you create 1,000 of this wave. That's the frequency. The relationship between time period and frequency is, time period is reciprocal of frequency. Okay, so T is 1 over F, just like in simple harmonic motion. And we also talked about this last time. So this is the relationship that gives you the height of a wave for a traveling wave. So here, this formula is for a snapshot graph. So this is the height at a particular time instant, okay, for a still image. So we took this picture at one particular time, and it is not moving. It's moving, but it's at a particular time, a constant time. So time is constant here. But assume that the wave is moving, okay? So, and it's also changing the position. Then you are changing both position as well as time. So again, this one is at constant time. The time is constant here. That's why we don't have any time here. So at a particular time, you have this formula for the height. But if you are trying to find the height of a moving wave, not at a particular instant, then this formula will give you the height of the wave. So here, x is the position, okay, where you are looking at. T is at what time you want to measure the height. Okay, so x is position. For example, if I'm moving like this, x would be my position at here, and then t would be the time. So starting from 0, how much time passed since I moved from the beginning. So that's the time, and x is how much distance I traveled from the beginning. Lambda is the wavelength, distance between crest to crest. T is the time period, time it takes to move from crest to crest. And A is amplitude. Okay? So this is the wave, this is for the wave that is moving to the right. If a wave is moving to the right, then that's the formula. If it is moving to the left, instead of negative, you put positive. Okay? And this is very fundamental relationship. You will see this over and over all the time. So we know that velocity as distance over time. So we learned this in physics 1. Definition of velocity or speed. Speed is distance over time. And distance, okay? So if we consider lambda to be the distance, so let's go back. If we consider from here to here, okay? So starting from here, the wave, you start from here, and then this wave is moving forward, and then it reaches here. So starting from crest up to crest, okay? So that distance is one wavelength. And the time it takes to cover that distance is capital T. Okay? So distance is lambda from here to here, and time is capital T. Okay? So if you plug distance to be lambda, then time would be time period. Okay? And we know that 1 over time period is frequency. Okay, so we just learned that here. So time period is 1 over frequency, and if we rearrange this, we'll get frequency to be 1 over time period. So frequency is 1 over time period. So 1 over time period is frequency. So the velocity of the speed of the wave is lambda times f. Okay. So speed of any wave is given by wavelength times frequency. This is very important relationship. That gives you how fast a wave is moving. If you know the frequency and if you know the wavelength, you multiply the two quantities and you get the speed of the wave. So again, like I said before, any source that does this back and forth motion produces sinusoidal wave. For example, sound, this is the speaker. Okay, so when speaker vibrates, it vibrates the air molecules in the surrounding. During the motion of the molecules, you will clearly get two regions. One with denser region, other one is less dense region. So denser region will have higher pressure because the molecules will be bouncing back more frequently. Okay? So they will be bouncing more frequently with each other, so you'll get more pressure. Here, because there is less molecules or air particles, there's less pressure. Okay? So you have more pressure region and less pressure region, and this changes continuously. So at one instance, this becomes more pressure region, and in the next instance, it will be less pressure region because it's doing back and forth. So these molecules are doing back and forth, back and forth. So at one instance, you get more molecules here. In the next instance, you'll get almost no molecules. So this is also kind of sinusoidal motion. That's why we can represent this by the sinusoidal curve. Okay? So in this sinusoidal curve, this is the amplitude, okay? Amplitude of the molecules. So let's consider a molecule starting from here. These molecules move maximum up to that point. So this is the amplitude, okay? Which is that. And then it goes back, okay? So that should be somewhere here, sorry. Let's say there's a molecule here, okay? Initially. So that's the original point, okay? Original point. Let's say I'm here, okay? I move this way, that's the maximum, okay? That's maximum. And then back again, okay? And then to this point, that would be negative maximum, okay? Negative pressure, and then back again, like that. So you have this kind of sine curve that has maximum pressure, so you have maximum pressure, zero pressure, and negative maximum pressure. So this maximum pressure region is called compression region, and then less maximum pressure, or the negative pressure region is called rarefaction region. So rarefaction region is for this one, and this is compression region, which is also called condensation. And the loudness of the sound depends on the pressure. Okay? If you are at this region, you will hear the sound louder because there is more pressure. That will give you more pressure in your ear. So when this region hits your ear, you hear louder sound than that region. Okay. So let's talk about the energy and intensity of a wave. Before we talk about energy and intensity, we'll talk about waves in higher dimension. So far we talked about waves in one dimension. So what I mean is, if I vibrate something, if I vibrate a string, the wave you produce is one-dimensional wave. Okay, so this is one-dimensional wave in one dimension, because the medium here is one-dimensional. Now, if you drop a stone on a pond, then the pond is two-dimensional. Okay, it's a surface. then the wave produced would be two-dimensional wave. So the wave produced on a surface is two-dimensional wave. For example, let's look at this. So this is a pond or some kind of water surface. If I drop water on this, I will produce this surface wave. Okay, so this is two-dimensional wave. Now, this is just a representation. You see this brighter part. This brighter part is the crest. Okay, it's the upward motion of the water molecules. This dark one is the downward. Okay, so this dark one is trough, and this brighter one is crest. Okay, so when you drop water, drop some object or a drop of water in some water surface, it does up and down motion, up and down, right? Up and down. So up and down, and then up and down and down. So it's up, and then dark one is down. So up, down motion. So up one is the crest, this brighter one, and darker one is again trough. The depressed one is the dark one. Okay, and close to the source, if you look at this, it's very curvy. Okay, it's highly curved. But as you go far and far, it gets less and less curved. And if far away from the source, it will look like a straight line. Okay, here, highly curved, less curved, less curved, less curved, and then far away from the source, it will be more or less straight. You see here, it's less curved than here. Okay, so less curved than there. Do you guys see that? You compare the wave here and here. The wave here is less curved than here. It's highly curved. See this curve? Here, less curved. And as you go far and far, the curviness decreases. Okay. Now, this is, again I said, this brighter part is crest. This is crest, so one crest to another crest. So distance between this crest and another crest is wavelength. Okay, let me pause this for a second. So you see here the distance between crest and crest. Okay, so that's crest, crest. That distance is wavelength, one wavelength. Or you can also say from here to here is one wavelength, crest to crest. Or you can also say from here to here, bright to bright, is wavelength. Or you can also say distance between dark to dark. Okay, so this one to that one. That's also same thing as distance between bright to bright. Exactly same distance. Okay, dark to dark is also wavelength. Now we can represent this in a simpler picture. Okay, this is more realistic, but we can make it a little bit more simpler. So like this. So this is the source, and the wave is moving outward. Okay, it's growing. So this curve or the circle, this circle represents the crest. Okay, so all these crests are represented by circles, and the distance between one circle to next circle is wavelength. Distance between one circle to another circle is wavelength, lambda. And these circles are called wave fronts. Okay, so these are the wave fronts. So one wave front, another wave front, another wave front, another wave front. Okay. So you start one wave front here, and that wave front will expand, move outward with some velocity v. Okay. So the wave front is moving outward at some velocity v. And again, this is the representation of the ripples you produce in a pond or some kind of surface. Not just pond, but if you place some kind of instrument, like a two-dimensional instrument, drum or something, you produce this kind of wave. Okay, this ripple produced in the drum. It goes up. There's a upward region and then downward region, upward region, downward region. Now again, like I said before, if you look at this wavefront from far distance, let's say you are here, and the wave is moving towards you, somewhere here, the curvature will be very, very less, very, very small. Okay, so curvature will be very small. It will be almost a straight line. Okay, so far away from the source, the wavefront will look like a straight line. So this is wavefront at far distance. So again, imagine that you are looking this from far distance. So this will look like that straight line. So it's only showing a part of the whole picture, okay? Just a part. So if you extend this, it will look like that, okay? Like that. You make a big one, it's a big circle, but it's only a part of the big circle, which is a straight line. So that's the two-dimensional wave, a wave on a surface. Now in real life, we also very often come across wave produced in a space, in 3 dimension. So when I'm speaking, I produce the wave in all direction, okay, all direction, not just a surface. Like if I drop water, I mean I drop some kind of rock on water, I produce this two-dimensional wave. But if I produce sound in air, I produce sound in all direction. So when I'm producing sound in all dimension, all direction, then in that case, the wavefront would be a sphere. Okay, so like there's a sphere around me. Okay, so I produce a small sphere in the beginning, small sphere, and then the sphere grows outwards. Okay, and I produce more and more sphere. So instead of circle, I produce sphere. Okay, so again, I produce one sphere, it goes out, another sphere goes out, another sphere goes out. So although you cannot see the sphere here, but this is producing a sphere, okay? It's only a part of the sphere. So let me see if I have a picture of the sphere. So that's the source of sound, or it could also be light, and it produces a sphere. And this sphere grows as it moves, as it propagates in space. Okay. So you have one sphere, and in the next instance you will produce another sphere. In the next instance, and you will produce another sphere. So distance from one sphere to another sphere is wavelength in this case. Okay. So this would be one sphere. This would be another sphere. This would be another sphere. This would be another sphere. So in each of the spheres, you have this particular region. Okay? This high density region or high pressure region. And the distance between one high density region to another high density region, or crest, this is crest, to another crest. Okay? So each sphere, surface of each sphere is a crest. So this is a crest, another crest. Distance between crest to crest is wavelength. Okay? And again, just like in two dimension, if you go far away, so this is wavefront, if you go far away, now the curvature will decrease as you go farther and farther. the curvature will be less and less. And far away from the source, you will see the wavefront to be a plane instead of a sphere. Okay? So this is a small part of the sphere. Okay? So you have a big sphere, okay? And that's a small part of the sphere, and that's far away from the source. So this is one sphere, this is next sphere, next sphere, next sphere, next sphere, and this is what we call plane wave. Okay? So this is plane wave. And this is part of spherical wave. Okay? This is the spherical wave. So here, this is a spherical wave, and far away from the source, this spherical wave will look like plane wave. So this spherical wave becomes a plane wave. So this is crest, another crest. Distance between crest to crest is wavelength. So, any question? Okay, so in the very beginning, we discussed that waves transfer energy from one point to another point. Okay? So the main purpose of wave is to transfer energy. So, and when we talk about energy, we use a term called intensity. Okay? Intensity tells you how big is the energy passing through some surface. Okay? How much energy is passing through some surface. Again, traveling wave transfers energy from one point to another point. And power, so to define intensity, we need a term called power. So what is power? You know power from physics 1. Power is defined as transfer of energy per second time. Right? So for example, you have a bulb or some kind of light source. If you see the rating of the bulb, you will see 100 watts, 60 watts, 500 watts. What does that mean? That means how much energy it is transferring from electrical source, electrical energy to some other energy. Okay? So transfer, the rate at which energy is transferred is the power. So faster a source transfers the energy, more power it has. Okay? You can also think about your own body. So the faster you can burn energy, the more power you have. Okay? So power is how fast you can burn energy or transfer energy from source to some outward surrounding. So power is basically energy over time. Okay, energy over time. And the power that passes through some area tells you how intense the wave would be at that point. Okay, so for example, let's say at this point I'm focusing that light in this much area. Okay, and now if I somehow change the focus and then I focus that light in a smaller area. So which one would be more intense? Like light over this much area or light over a small area? Smaller area. Like if you focus light with a magnifying glass over a small area, you can actually burn a piece of paper, right? So if you focus the sunlight on a small spot with a magnifying glass, it will be very, very intense. That can even burn your skin. So intensity depends on the area over which you focus the power. Okay, if you have a smaller area, then the wave is more intense. If you have a bigger area, then it's less intense. So intensity at any point on the sphere would be power, how much power it produces, and the area over which you are calculating the intensity. Okay, and this also has the consequence on our seasons. Okay? During winter, the sun falls over a wider area. That's why it's less intense. But in summer, it falls directly on the area. That's why it's more intense. Okay? Because the Earth is tilted, so during the winter, it falls over more area, creating less intense sunlight. Whereas over the summer, it's tilted in such a way that it will fall on more region. The SI unit for intensity is watt per meter squared. Okay, that's the unit of intensity. Again, wave focused on small area has higher intensity than if it were spread out. So here is an example. Let's look at the first example. So it's question 2. So we have a laser beam, and the laser beam has the power of 1 milliwatt. Okay, so laser beam. So this laser beam has power of 1 milliwatt. That means every second it can convert 1 millijoule of energy, electrical energy to light energy. So this is converting 1 millijoules of electrical energy to light energy. So that's the power of this laser. And if I point this laser over that much area, that much diameter, the area with that much diameter. So you see that spot. So this spot has some area, and the diameter of that area is that. Okay? So what would be the intensity of this laser point over that region? So what's the intensity at that point, that area? So intensity is given by power over area. Power is that. Okay, so I change this milli to watt by dividing with 1,000, and then area is pi r squared. Now, this area, when you use area here, if it is a surface area, if it is a small area like this, then you use pi r squared. But if you are using a three-dimensional area, you would need to use 4 pi r squared here. So the formula for the spherical area of a sphere is pi r squared. But for a tiny area like this, you can use pi r squared. Okay, so that's the intensity. Okay? Now, sometimes instead of using intensity, we use something called decibel when we need to represent the loudness of sound. Because okay, so before we talk about loudness, so again, intensity is power over area, and in this case, if it is a sphere, then we use 4 pi r squared. That's something we need to keep in mind. Okay, for spherical area, it's 4 pi r squared. So now let's talk about loudness. Okay, so more the intensity of sound, louder the sound is. Okay, so here versus here, so the sound is falling over a smaller area here. Okay, so that means there is more intensity of sound here. Here it is falling over bigger area, so less intensity. Okay, if you see the arrows here, there's more number of arrows passing through here. That means more number of arrows means more intense sound. Less number of arrows passing through the surface. So there's only 2 arrows passing here. There are 3 arrows passing here. No, actually, this is not showing very clearly, but if I draw more arrows here, what you will see is there will be more arrows here than here. You will see that in chapter 17, electrostatics. What that means is intensity depends on the number of arrows passing, number of lines passing, which we call flux. Okay? But for now, you can just think of this as less the surface area, more intense the sound. Okay? So instead of using intensity, sometimes we use something called decibel. Okay? The reason for that is so when the intensity of a sound increases by 10 folds, okay, so let's say you have the intensity of sound to be let's say your intensity of sound is 5 times 10 to the 5 watt meter square. Okay, that's the intensity of sound. Now, if you increase this by 10 folds, okay, 10 folds, 10 times, it will be 6 watt meter square. So, if you increase this by 10 folds, then only the loudness you perceive will be doubled. Okay, so let's say you perceive some kind of loudness for this intensity. Okay, so that's you hear this to be some amount of loudness. Let's say that's loudness 1. And then, if you make it 10 folds, then the intensity you perceive, the loudness you perceive will be doubled. Okay, so loudness would be doubled. If you increase this by 3 folds, 10 more folds, 10 more times, then this would be now 3 times louder than before, than this one. So for each amount of increase in loudness, you need to increase the intensity by 10 folds. So it's a big number. So when you have big numbers like this, like 10 folds, 10 fold, 10 fold, so instead of using this big number, we use something called log scale. Okay, we express the numbers in log scale. So when we express the intensity in log scale, we call it decibel scale. Okay, so loudness, that's why the loudness is measured in decibel scale. I think we are out of time, sorry for that. I will continue this next time. You guys can stop me once I'm out of time. Sometimes I don't keep track of time. We'll continue this next time.